So for our digital electronics project, we decided to make an LED cube. This LED cube has two different player controls, and each player has the ability to move their individual LEDs through the cube.
Now, as you can see, this button on the left controls the x-axis. This button on the right controls the y-axis. This button closest to me controls the z-axis.
So the way the LED cube works logically is we have a bunch of these LEDs which are actually light-emitting diodes. These diodes have all their anodes hooked up in the individual planes and up to a resistor. And then the cathodes are hooked up into the column. The result of this is that when you give a logical high to the plane and a logical low to the column, it puts the LED into forward bias, which turns it on. All the other LEDs are in reverse biased, either because of the plane is too low or because the column's too high. Each of the planes represents one position on the z-axis, and the columns together is both the x and the y-axis, which needs to be split out later into using the NAND matrix.
This project wouldn't be possible without our NAND matrix, a 74X00 Ti chip, combining the x and y axes into columns. Since there is inverted logic on the columns, we used a NAND gate instead of an AND gate. So, all these LEDs on this column right here are all on logical highs. But this one LED right here, which is on a logical, or on a low.
So the next thing I should mention is the counters we used. You've seen decade counters before, these 4017 chips, in classes such as Engineering 101. Essentially what they do is every time they receive a pulse, they increment the light one position. Now in 101 we normally used a clock for this, but in this class we decided to use buttons, which is what allows the LEDs to move. These buttons use pull-up buttons and pull-down resistors, which means they start out as a logical low, but then whenever you press the button it switches to a logical high, which gives a rising edge pulse to these decade counters. Each player has a total of 3 decade counters, one on the z-axis, one on the y-axis, and one on the x-axis. So for each group of these 3, you see there's a player 1 counter and a player 2 counter. The last thing to mention with these buttons is these capacitors. These buttons are a little bit finicky, so every once in a while when you press the button, instead of just sending over 1 pulse, it sends 2 or 3. These capacitors essentially prevent that by making a really short pulse just ignored.
So the last thing we're going to talk about is player select, which determines which player is shown on the cube. Using a 2-to-1 multiplexer TI-74X257 chip, located right here, at a logical high, we are able to select player 1, which is David. And then at a logical low, we are able to select me, which is player 2. Now, the way we were able to get to multiplayer was using a 555 chimer chip, which we learned in Engineering 101. Now, through the circuit we found online, we know we needed a resistor and capacitor to produce a frequency of 71 Hertz, which we thought was enough to be able to get past the human eye's requirement of 60 Hertz, 60 Hertz so that you can't see the LED flipping back and forth. Now, as you saw, David was flipping it manually, which we could tell as a human that it was flipping back and forth, but with this 71 Hertz, you cannot tell that the LEDs are flipping back and forth.
So in conclusion, we think this is a really good project for digital electronics because it uses 3 of the major things we discussed in class. The first thing is uses diode logic, which is the LED cube. These LEDs, when they're on, are in forward bias region, and then we turn them off using multiple different ways of reaching reverse bias.
The second way was through buttons and switches, using pull-up and pull-down resistors. So as you can see, the buttons are using pull-down resistors, and the dip switch right here is using a pull-up resistor.
The last relation to digital electronics is transistors. While you don't see any transistors directly in our circuit, based on schematics we found online, all of these logic chips use transistors internally.